So let's get started. Today we are going to start new chapter, which is chapter 5, equilibrium for a rigid body. If you do remember, uh, in chapter 3, we talked about equilibrium of a particle. And in the first lecture, if you do remember, we have a difference between a particle and a body. So in chapter 3, we discussed the equilibrium of a particle, and now in chapter 5, we are going to discuss the equilibrium for a rigid body. We are going to talk about 2 points. Point 1 about conditions for rigid body equilibrium. So we are going to say if a rigid body is in equilibrium, what does it really mean? And what are the conditions in order to satisfy the equilibrium of a rigid body? Then we are going to talk about the support reactions, and finally we are going to discuss how we are going to develop free body diagram. So recall in chapter 3 we talked about equilibrium of a particle. And in order to satisfy the equilibrium of a particle, we said that the summation of the forces acting upon the particle, either in 2D or 3D, summation of the force vectors should equal 0. And that equation here, it could be divided into 2 parts. The summation of the forces in x should equal 0, and the summation of the force in y-axis should equal 0 if we are dealing with 2D situation. So here we have a coplanar system. All the forces lies in xy plane. So I'm going to use only 2 equations. While in 3D, here we have a particle is in equilibrium, and we have forces acting on that particle. And then that equation, it could be divided into 3 equations. The summation of the forces in x should equal 0. Summation of the forces in y should equal 0. And finally, the summation of the forces in z direction should equal 0. That's what we have discussed about the equilibrium of a particle. But now we need to know the conditions for equilibrium of a rigid body. So in the first lecture, we discussed the difference between a particle and a rigid body. We said that the particle has a mass, but no size. So if you remember, when we were dealing with the particle, we used to consider the weight of the particle itself. But we don't deal with the size of that particle. We ignore that part. But when we are dealing with a rigid body, we are going to deal with the mass plus the size of the rigid body. And for example, here we have a steering wheel here. Assume that you apply a force here. So if you apply a force at that end here, you are going to get rotation. Okay, so as a result, if I apply a force here, I'm going to have rotation about the point O. And the distance from here to here, if the whole distance is d, then the distance from here to here is going to be d over 2. So I'm going to get a moment about that point O, and the value of that moment is d over 2 times f. And the direction of the moment is clockwise. So the steering wheel is going to rotate counterclockwise. And if that was a particle, if I apply a force as a force in different direction, then you might think that the body is going to be in equilibrium. Because if I have a force F here and I have a force here down, the summation of the forces is going to equal 0. And the, uh, the, the rigid body here, it should be in equilibrium because the summation of the forces should equal 0. But this is not a particle. If that was a particle, then you are going to say the summation of the force is going to equal 0 and the particle is in equilibrium. But here, since this is the rigid body, which means that I have a size here, I need to take the size in our consideration, then we are going to find out that even though the summation of the forces in y direction is going to equal 0, but the steer wheel is going to rotate. Because here I'm going to have moment, which is counterclockwise. And here also I'm going to have a moment, also it's counterclockwise. So even though the force, summation of the force equals 0, but I'm going to have a moment. And we call this case couple moment. And the couple moment, when I have a parallel forces, so that force here is parallel to that force. And they have the same magnitude, but the direction is opposite. So the direction of that one is different from that one, even though the magnitude of the force here is F and here is F. The summation of the forces is going to equal 0. If you are going to say that summation of the forces in y direction is going to equal 0, you are going to have a tendency for rotation. And we call this couple moment. So I could replace that force and that force with a moment that equal F multiplied by D. D is a distance from here to here. So if you are going to say that summation of the forces in y direction, you are going to have F and minus F, and summation is 0. But if you are going to take the moment about that point here, let's call it O. So I'm going to take the moment about the point O. I'm going to find out that F times D over 2, which is positive. And here I'm going to have F times D over 2, which is also positive, because this one here is going to produce a moment which is counterclockwise. So take this as a common factor. D over 2 plus D over 2 are going to have D. And that is the moment of a couple. You have forces. Summation of the forces is 0, but you are going to have a rotation. And we can notice here, because we have a rigid body, that equation does not give us equilibrium. You could also put a force here and a force there with the same amount. And also the summation of the forces in x direction is going to equal 0, but you are going to have a rotation. So I cannot say that the rigid body is in equilibrium because you have rotation. If the body is in equilibrium, it means that I don't have movement in x or in y or in any direction. And also I have new condition, which is I don't want any rotation. And in order to satisfy that conditions, the moment about the point O should equal 0. So if that body, if I calculate the moment about the point O, and the resultant moment here came out to be 0, that means the steer wheel here is not going to rotate, and it means that now the rigid body is in equilibrium. So for this rigid body, even though the summation of the forces in x equals 0, in y equals 0, the body is going to rotate. That is why we need a third equation for equilibrium of a rigid body. So what we have been studying in the previous lectures, we learned that if we have a body like that, and that body, it has forces and it has moments, and I have, let's say, O is a point of rotation. We'll learn how to calculate the resultant force. If I have a number of force, we'll learn how to calculate the resultant of the force, and also we learn how to calculate the resultant moment. But for that body to be in equilibrium, the resultant force should equal 0, and the resultant moment should equal 0. So mathematically, the equilibrium of a body is expressed as the summation of the forces acting on the body should equal 0, and the summation of the moment at any point here in the body should equal 0. So the difference between the particle and the rigid body, in a particle, I'm going to ignore the size of the particle. I'm going to deal with the mass only. And that equation alone is going to bring the equilibrium for the particle. But when it comes to rigid body, the size is, we're going to take the size into our consideration. And in order for the body to be in equilibrium, we need to satisfy that condition, which is a summation of the forces should equal 0, plus the new condition, which is the summation of the moment about any point should equal 0. So we have new conditions here, which is different from the equilibrium of a particle. And like I said in the previous chapter, we'll learn how to calculate the resultant forces. And we have done that in order to prepare us to deal with the equilibrium of a body. So the conditions, if the body is in equilibrium, it's mean the summation of the forces should equal 0, and the summation of the moment should equal 0. If I'm going to deal with 2D problems, I'm going to say that those equation here is going to be breakdown into summation of the forces in X should equal 0, summation of the forces in Y should equal 0, and the summation of the moment about any point should equal 0. So if you are going to deal with 2D problems, I'm going to use these three equations. If I'm going to deal with 3D problems, I'm going to use those equations. So here I'm going to have summation of Z equals 0, additional 1 here, and also the summation of the moment about X-axis should equal 0, and the summation of the moment about Y-axis should equal 0, and finally the summation of the moment about Z-axis should equal 0. So here, 2D problem, which means that all the forces lies into X and Y axis, and here we have 3D problem. We have forces in X, we have forces in Y, and we have forces in Z. In 2D problem, we are going to have three equations. In 3D problem, we are going to use 6 equations. And in order to put a rigid body, we need to support them. And that is why we have support reaction. And we have many types for that. For example, here we have a beam. We call this a beam. And in order to that beam to be in equilibrium, I need to support it. For example, here, the beam, it has been fixed inside that wall, so that the beam is not going to move down or to move to left or to right, and also is not going to rotate. So here, since the beam is fixed into that wall here, so that beam, especially that section here, it's not going to rotate like that. It's not going to move here or here. It's not going to move up or down because of that support reaction. And similarly here, I have a beam. It has been supported from here and supported from there also. We are supported from here so that we are not going to have any rotation, because this type of support, it's not going to develop resistance for rotation. That is why I need to put a link like that, so that the beam here is not going to rotate. Here we have another body, we call this truss, normally you are going to use a truss as a bridge in order for the people and the cars to move from that side to that side. And for example, if we don't provide support here, what do you think will happen? Then the bridge here or the truss is going to go down here. Or also, let's say that if I don't have resistance in that direction, maybe that bridge is going to move here or there. And also, let's say that if I don't have support here, I have only support from there, then the bridge is going to rotate. So also here and here, we are going to use the support reaction. So the support reaction is going to provide stability for my rigid body. So if the support reaction is going to bring stability for our structures, it means that they have reaction. So if I'm going to fix the beam here into the wall, that means now the wall, it has reaction. Yeah, for example, the wall is going to have resistance for rotation. And I want to make sure that the wall have enough stability in order to support that rotation as a result of that force. Since I have force here, if I want to calculate the moment at that point, I'm going to have a rotation, which is 1,200 Newton times 2 meter. I'm going to have a moment at that point, and we should have a resistance opposite to that one in order to bring the stability for the beam here. So how to deal with the support reactions? We have a general rule for that, 2 rules. If you understand those general rules, you are going to be in a safe side. So the first rule says that if if you have a support that prevents translation of the body in a given direction. So if you have here we have support reaction, here we have support reaction, here and there. If that support reaction is going to prevent the body from moving in a direction, for example, if that support here is going to prevent the body from moving in that direction or in that direction, then that support reaction is going to develop a force in that opposite direction. And also, if the reaction is going to prevent a moment, for example, here, the reaction here, the support reaction here is going to develop resistance for rotation. So if you have support that to prevent the rotation here, like this example, sometimes, like you can see here, I have a beam, and here I have a ruler. It's like a small ball here. So if you are going to have a small ball, and if you apply a force here, then the body is going to move in that direction. That means the roller is not going to provide reaction in that direction. But if I apply a force in this direction, and I'm going to have a roller, then the body is not going to move down because of that roller. So in that case, I have reaction in opposite direction. And here I have what's so-called pin. If I apply a force here and I have a pin here, then the body is not going to move in that direction. And also, if I apply a force here, it's not going to move in that direction. So I'm going to have reaction in that direction here and in that direction there. Here, in case of the wall, I'm not going to have movement either in that direction or in that direction, and also the rotation is going to be prevented. So basically, we have 3 types. We have the roller. So this is the roller. And if you are going to know the reaction, you are going to take this out, and then in order to replace the, the reaction, I'm going to put a force like that. So instead of that roller, we are going to have reaction here. But I'm not going to have reaction here because the roller does not support the movement in x-axis here. So we have the roller, just like a small ball. It has reaction in x in y-axis, but it does not support the transition of the body in x-axis. So if you want to know the reaction of the roller, is going to be perpendicular to that plane. So instead of the roller, I have reaction. So the support reaction, it provides reaction like that one. The other type, which is a pin. If you can see here, this one, we call this pin support. So if you want to understand the pin support, here we have the components of the pin support. We have the member. So if this one is a beam, if you cut from here, and if you are looking from there, you are going to see the side view is going to be like that. And then we have the leaves here in order to put the member like that. And then I'm going to put the pin. So I have the member, I have the leaves, and I have the pin. From that view is going to be like that. We have pin support. This pin support is different from the ruler. In that case, we are going to have resistance in x-axis and in y-axis. So if I apply a force like that, then I'm going to have reaction from here. And if I apply a force here, the pin is going to support, is going to provide reaction opposite to that one to bring stability. So if you are going to use a pin support, you are going to have reaction in X and reaction in Y. If you are going to use roller, you are going to have reaction only in Y. While X, the body is going to be free to move in X axis. And finally, we have the fixed support. Like this one here, I have a beam and the beam is fixed to the wall. So in that case, if I apply force like that, then I'm going to have reaction in y-axis. And if I put a force here, I'm going to find resistance in x-axis. And that force, of course, is going to cause rotation. And also, I'm going to have resistance to that rotation. So the fixed support is going to provide reaction in X and in Y and reaction for the moment. While this one here, the roller, if I'm going to have rotation, so I apply force here, this part is going to rotate. So here I'm going to have angle. And if I apply force here, that body is going to move to that direction. But if I apply force here, that part is not cannot move down. That is why the ruler only provide reaction in that direction. And if you put the pin support instead of a ruler, you are going to have resistance in X and in Y. And if you put fixed support, you are going to have resistance in X and in Y and resistance to a moment. Here are the basic support reaction types. If you understand this, you will be able to understand the next types. We have like 10 types. They depends on the same idea here. So if you understand this, you will be able to understand all the different types of support reaction. I'm going to stop here. Tomorrow we are going to build on what we got right now. And it's very important part of the course. So make sure that you have a good understanding for that. So I'm going to, like I said, I'm going to stop